This is Advanced Algebra Lesson 8-2, Inverses of Relations. The big idea of this lesson is every relation has an inverse. Some of these inverses are functions. But before I even go into the inverses, let's refresh our memory as to what it is to be a relation. A relation is just simply a set of ordered pairs. So if we're going to do an inverse of ordered pairs, let's think about what that might mean. We are just basically switching the coordinates of each ordered pair. So our x's become y's and our y's become x's. So if we look at this example 1, we're going to let q equal the set of points -2, 5, -1, 7, 0, 3, 1, 7, and 2, 1. To find the inverse of q, all we're going to do is switch the values of x and y. So if h is the inverse of q, then h is now 5, -2, so all we did is flip-flop these two coordinates, or the x and y values here for this coordinate. We flip this -1 and 7 to become 7, -1. Flip the 0, 3 to 3, 0. Flip 1, 7 to 7, 1. And the same thing with 2, 1, it became 1, 2. Next, I'd like to explore domain and range of a relation and its inverse. The domain of a relation and its inverses are switched. For example, the domain of f is the same as the range of the inverse of f, and the range of f is the same as the domain of the inverse of f. So we have an inverse relation theorem. So suppose f is a relation and g is the inverse of f. Then, if a rule for f exists, a rule for g can be found by switching x and y in the rule for f. The graph of g is the reflection image of the graph of f over the line with the equation y equals x, and the domain of g is the range of f, and the range of g is the domain of f. Okay, that can sound kind of confusing, so let's take a look at an example and explore that further. In example 2, I'd like to look at the function with equation y equals -2x squared. And we're going to say the domain is the set of all real numbers. So what is an equation for the inverse of this function? So if you go over here to our inverse relationship theorem, it says that if a rule for f exists, a rule for g can be found by switching x and y in the rule for f. So here's our x and y, and I'm going to switch them. So now this is my inverse of the first one. Part 2 says they want you to graph the function and its inverse on one set of axes. I chose to graph this by hand just because I wanted to explore the relation piece from above by switching our coordinates. So I quick made a table, values for x and y for our original function. As you can see here, I just generated some values and I graphed my parabola. As you can see, the domain of this is all the set of all reals, and the range of this would be the values for y that are less than or equal to 0. So now if I go and I graph the second equation, our inverse of the first, we know that we can, as above, switch our x and y coordinates. So I did that. And that fits number 2 of our inverse relation theorem. And that states that the graph of g is the reflection image of the graph of f over the line with the equation y equals x. And so that equation, y equals x, follows this black line that I'm putting in here. You can see that these are definite reflections of each other over the line y equals x. So the last part of this inverse relation theorem is that the domain of g is the range of f, and the range of g is the domain of f. So if you look at this, we already said the domain of this is all reals, and the range is the values for y which are less than or equal to 0. Now if you look at the blue and what the domain of that would be, that is going to be the values of that are less than or equal to 0. So that would be your domain. And your range is going to be all reals. So those did a reverse also. So then the last question here is the inverse a function? Why or why not? Well, if you look at the first one, that was a function. We could definitely pass the vertical line test. But if you look at the blue here, our new graph, that clearly does not pass the vertical line test. So that tells us that it is not a function. So the inverse is not a function. So we have the vertical line test that I talked about before. If you did not want to apply or want to graph something, the inverse, you can use the horizontal line test on the original. So I could test this one, the red graph, with a horizontal line test, and you see that it does not pass a horizontal line test. So if you did not want to graph the function's inverse, you could test the original function with a horizontal line test. Let's take a look and explore this a little bit further. Here I have two functions graphed below. So is the inverse of each function a function? Explain your reasoning. Since this is my original function, I can instead of doing the vertical line test like I would do to test this graph to see if it was a function, if I want to see if the inverse of this is a function, I can apply the horizontal line test. And as you can see, I never hit more than one point at a time, so my inverse is a function. So inverse is a function. Okay, and so then state the domain and range of each function. The domain and range of this is all reals. Domain and range is all reals. So then the domain and range of the inverse would be all reals also. Okay. Now let's explore number 2. Is the inverse of this a function? Does this pass the horizontal line test? As you can see, I have more than one value hitting the line, so this does not. So the inverse of this is not a function. And then state the domain and range of each function. So the domain of this function appears to be all reals, and the range appears to be values that are values for y such that y is less than or equal to 2. So for the inverse, we're going to flip-flop. So that means the domain is going to be values for x such that x, is less than or equal to 2. And the range is going to be all reals. This concludes Lesson 8-2.